Lukas Palatinus studied mineralogy and geochemistry at Charles University in Prague. During his PhD at the University of Beirut, Germany, he focused on crystallographic analysis of modulated structures. Later, during the postdoctoral stay at the EPFL Lausanne, Switzerland, he developed the program SuperFlip for the solution of crystallographic phase problem for periodic and aperiodic crystals using the iterative dual space algorithm. Since 2009, Professor Palatinus is the head of the group of electron crystallography at the Institute of Physics of the Czech Academy of Sciences in Prague. He and his co-workers are developing methods for crystal structure analysis from electron diffraction data, with the main focus on the structure refinement from 3D electron diffraction using dynamical diffraction theory. Lukas will present today his lecture entitled 3D electron diffraction for charge density analysis. What are the challenges? Lukas, the screen is yours.
Well, thank you for the invitation, and thanks to everybody who still is online. Thanks for your perseverance. This is a long, almost a series of lectures, but at the same time, I think it's a very nice combination, at least for me, because Paulina did say a lot of interesting information about charge densities and a specific of charge density analysis from electron diffraction data, while Richard focused quite in detail on the dynamical effects in electron diffraction data. And so what remains for me to do is to do a synthesis of these two aspects and discuss somewhat how far can we get, what is the current status of our ability to extract charge density information from electron diffraction data if we take the dynamical effects into account. So, just to start, I will say a few words about the experiment, which has not been discussed. Well, it was discussed in detail by Richard, but I want to point out the differences. So we are, it's like, you know, the journey there and back again. We started, Paulina talked about the standard diffraction, that means parallel beam and spotlight diffraction patterns. Richard then talked about the technique using convergent beam and showed very convincingly how detailed information one can get from this convergent beam electron diffraction approach. And I'm coming back to the point or spot diffraction patterns again. So what we do is actually a very simple experiment. Conceptually, take a crystal, shine a parallel beam, collect the diffraction patterns in either in small steps or during a continuous rotation of the beam, and then what we obtain is a three-dimensional representation of the reciprocal space, of the intensity space. The reason we are not using the digital Lagbed approach that Richard explained is well, manifold, and I think the most important one is that we want to look at crystals that are way too complex and way too beam sensitive to allow an approach like this, and also for the digital Lagbed data collection, or to get these nice, very well structured patterns, the crystal really needs to be perfect or essentially perfect. While real crystals are not always perfect, and we still want to extract some structural information from that, and spot patterns allow us to do that. This is another representation of the experiment. This is just to show that first, well, we may have some technical difficulties tracking the crystal, trying to follow the crystal as it moves during the tilt. At the same time, you see that the diffraction can really be beautiful. And this is something like real-time data recording with modern systems for collecting 3D electron diffraction data. So you see the experiment is really very fast once you find a crystal that you want to measure. So, well, there's a lot of history in electron diffraction, a lot of history of crystal structure analysis by electron diffraction, and I'm glad that Paulina mentioned at least a few really classical works related to charge densities, works of Avilov, Tsirelson, then later Philip Nakashima, and others. But for the 3D electron diffraction technique, we really have a well-defined point in history where the technique started. That was in 2007 when Utek Hopp and co-workers started or proposed this X-ray-like type data collection approach for electron diffraction. And then don't worry, I'm not going to go through all these points. This is just a collection of a couple of milestones, very subjectively possibly selected, that line up the path from the first experiment showing that it's possible to the last experiment, to the last results. Of course, there are more and more coming, showing that we can solve and refine structures with very high accuracy, very complex structures, and can do things like absolute structure and, as we will see today, also charge density investigations using 3D electron diffraction. So considering it's been 15 years from the first publication, I think it's a stunningly fast development. If you're interested in more details, there's a number of reviews that appeared in the last 2-3 years, but I can among them recommend these two. This one is really comprehensive overview of what happened until 2019. This one is a bit newer, focused more on chemists, so showing the power of 3D electron diffraction for a chemical audience. Now there are many others available now. One last point about the experiment. There are various types of data collection experiments. Here I summarized the 3 most important bits. So either you can do so-called static beam 3D electron diffraction, where you just position the crystal, take a pattern, tilt the crystal, stop it, take another pattern, and with small tilts, collect one pattern after another. This approach is the least optimal, but it's an approach that can be done on essentially any electron microscope and still provides data which are perfectly good for the analysis. The second approach that was very popular in the past because it allowed integrating data without having a very fast readout camera, that's precision-assisted 3D ED, where the crystal is again static, and then the beam is actually processing, and all the intensities during the beam precision are recorded, and like that we can get integrated intensities on a single pattern. And then the last technique, the one that is most often used nowadays, or it is more and more popular, that's continuous rotation 3D ED, and that is also the conceptually most simple technique, where you just tilt the crystal continuously and record the diffraction with a fast detector with fast readout. So then the readout is essentially negligible, and you collect all the diffraction coming from the continuously tilted crystal. So there are subtle differences between these two. There might be subtle differences in treating these data sets, but it is possible to use all of them and to extract information of the type that I will be talking about in the rest of this presentation. So I hope, I strongly believe that after Richard's presentation, nobody from the audience has any doubt that dynamical effects are important in electron diffraction data. They are important even if they are not visible. again, as Richard showed on his analysis of the silicon data, there are many clear proofs that dynamical effects are really important, and that's why it is really worthwhile trying to include them in the analysis. Still, if you for some reason don't want or cannot do that, it is possible to ignore the dynamical effects and use a technique that is called kinematic refinement for short, which means we collect electron diffraction data, integrate the intensities, and then pretend there are no dynamical effects. Process the data with standard X-ray software, software that was originally developed for X-ray diffraction, and then refine against intensities, assuming that the intensity is proportional to the square of the structure factor. This works. It's conceptually very simple. It's very fast. It takes seconds to make the refinement. Works for all types of 3D data. It's available in all the refinement programs, whether you prefer Shellix, Olex, Crystals, Yana, whatever. But the price to pay is that this is a relatively poor approximation, depending on the type of crystal, the thickness of the crystal, the perfection of the crystal. It may be more or less poor, but in any case, there is a very substantial approximation involved, and that's why it gives low accuracy and higher figures of merit from that refinement. On the other hand, of course, you can use dynamical diffraction theory to simulate the intensities. Again, as Richard said, the theory has been there for a long time. Richard and also we in our software are using Bloch wave method to calculate the intensities. And then the rest is actually the same. It's still standard structure analysis, structure refinement approach. The only difference is that the intensities are calculated not using this simple kinematical approximation, but using the full dynamical calculation. The advantages are obvious. It's more accurate. It's more sensitive to weak signals. It gives significantly lower figures of merit. The price to pay are longer computing times, although things are changing there as well. And if some of you have done some dynamical refinements in the past, there's been some, let's say, recent improvements that made the speed of the calculation faster by about a factor of 10 or more. So nowadays, even moderately complex structure takes something like at most a couple of minutes per refinement cycle. So we are talking about longer times than kinematic refinement, but definitely not many days of waiting. And well, currently it's implemented only in the pair of programs PETS2 for data processing and Yana 2020 for the structure refinement. So I said there is not a big difference between dynamical and kinematical refinement. There are a few technical differences. Because the orientation of the crystal is important, the refinement is using frame-based intensities, so we need to know which frame the intensity was on. We need to filter reflections based on their proximity to the level sphere. We need to refine the thickness and crystal orientation. Until recently, only precession diffraction data were available, but now also continuous rotation data can be routinely used for dynamical refinement. So that's not a big difference. And here on this picture, you can see the significant improvement you can obtain in the fit. This is experimental pattern. This is the kinematical approximation of the same pattern, and this is the dynamical one. You see already visually that the fit is much better, and if you calculate the weighted R value on these intensities, you see that you obtain a really significantly better fit. So this is a little overview of how much difference it can make for dynamical refinement. This is a selection of 8 structures, 4 of them inorganic, 4 of them organic, refined dynamically, kinematically. The red is kinematical, blue is dynamical refinement, and on the vertical axis there is refinement R value, and you see that on average we gain about a factor of 2 in the R factor. Here is the same thing done on as in form of a histogram. So this is a histogram of dynamical R values. This is the kinematical, and on average we are almost exactly 1/2 less in the R factors. So, but there is still a significant gap that we face in the R values that we can achieve. This is a little histogram of kinematic R values. This is a collection that I made some time ago. It includes inorganic and organic structures, and the spread of R values for kinematical refinements is rather big. These are the red bars, so you can see if you're really lucky, you can get close to 10%, but you can also be easily close to 30% or above. For dynamical refinement, it's much better, and I'd say when we are above 10%, we are somewhat disappointed with the result. So getting to 10 or a bit less than 10% is should be quite possible with dynamical refinement. But actually, what we expect, or where we would like to get, is somewhere here. That's the typical R value for X-rays. Well, maybe we would like to be even better, but this is the next step. And this gap here, so the gap between kinematical and X-rays can be to a large extent closed by including dynamical effects. But then there is a gap between the dynamical results and the X-rays. And there are several candidates for the reason for this gap. But I'm personally more and more convinced, and the evidence piles up, that the key difference is unaccounted for crystal imperfections. So we model the dynamical intensities assuming perfect crystal, but the crystals are not perfect. And again, in just a few slides, I believe I will show you a convincing evidence that this is indeed the case. So, with this introduction, let me get to the topic, or main topic of this lecture series, and that is quantum crystallography, or charge density analysis. But let's start it lightly, not directly looking at really charge distribution and subatomic or bonding effects. But let's first have a look at our ability to detect hydrogen atoms using electron diffraction. An interesting plot is this. This is the relative scattering power of hydrogen compared to carbon. And the gray line is for X-rays. The resolution here is in D star, so 1 divided by D. And the red line are electrons. You see that for X-rays, hydrogen very quickly loses its power, scattering power, while for electrons, hydrogen remains scattering relatively to carbon essentially constantly up to very high resolution. So in principle, hydrogen is more easily detected by electrons than by X-rays. In spite of that, for a long time, it was difficult to see. There are scattered mentions in the literature in the past. And then we looked into it a little bit in more detail in the year 2017. And again, illustrating the progress of the method. At that time, it was sufficient success to make it to a cover of Science. Now, 5 years from that, it's actually essentially routine, and nobody gets ecstatic by seeing hydrogen atoms in their difference Fourier map. The important point is that we can actually see hydrogen atoms nicely, not only in light atom organic structures, but also in structures containing heavier atoms. And one of the examples comes, I show here. This was done by Gladys Stetsiuk, here from Prague. She's our expert on difficult inorganic troublesome structures. And this is a structure of cartialite, a mineral that contains iron and arsenic. And it turned out that it contains 22 hydrogen atoms, 12 of them disordered, so they are actually half occupied hydrogen atoms. And you see in the difference Fourier map that there are actually hydrogen atoms, these half-occupied hydrogen atoms, quite nice visible in the difference map. So it was possible to refine the structure and locate the partially occupied hydrogens. And if you are not really impressed by seeing hydrogens next to arsenic, maybe you will be impressed by seeing hydrogen next to uranium. So this is another work by Gladys. This is uranium-containing mineral, and there is an OH group. You see in the difference map that the hydrogen is just sitting there. And I know that the refinement R value for this structure, the R ops, is below 4%. So not too bad. Okay, but we can do more about hydrogens than just seeing them. And it was already a bit touched or commented on by Paulina. But there is a question, where are the hydrogen atoms? And we know that in neutron diffraction gives us the distances that are pretty close to the, well, they are actually the real nucleus distance. For X-rays, because X-rays see only electrons, the refined distance is much shorter. And for electrons, actually it turns out that the refined distance is a bit longer. And that might be surprising a bit, but very soon we'll see why is that. And this is a plot of R value as a function of the distance of the hydrogen atoms in the structure from the optimal neutron distance. And you see that in all cases, these are several structures. The molecules or structures are shown here. Some are organic, some inorganic. And you see that in some cases it's almost no difference, while in other cases the difference can be up to almost 0.2 angstroms. This was observed several times. It was also observed in a single particle analysis, so cryo-EM analysis in this paper, where they already also analyzed it semi-quantitatively. And the reason why electrons see hydrogens further away from carbon, for example, is actually very simple. This is a little sketch. It's not very quantitative. It's using just Gaussian peaks. But in a neutral atom, the potential from the nucleus may be represented by this blue line, while the electrostatic potential of the electron around, or electron cloud around the atom, may be represented by this orange Gaussian. And what electrons see is the difference between them. So it's the positive potential of the core minus the negative potential of the electrons. And while neutrons see this, and X-rays see this. And now what happens in the bonded atom, the nucleus stays where it is, more or less, and electrons shift a little bit towards the bonded atom. So in this plot, a bit to the left. So the electron density shifts to the left. That's why X-rays see it closer to the bonded atom, but the difference shifts to the right. And that's why electrons see it further away from the atom. So it's very simple. It's a little bit unfortunate. It would be nice to see the hydrogens spot on where they should be. But as we have seen in the presentation by Paulina, there is quite a simple remedy to this, and that is using the transferable atom model. Or other, let's say, advanced ways of describing the crystal structure. And with that, I'm coming finally to the charge density analysis and its possibilities to use charge density analysis in electron diffraction. And the first step we can make is the one that Paulina described in quite a detail, and that is the transferable spherical atom model. So just to remind you, take the electron distribution of an atom from a database that has been typically calculated using DFT calculation, and replace the spherical independent atom in the structure by an atom deformed properly by chemical bonding. This has been tried by Paulina and her co-workers on several compounds. It was shown in in theoretical calculations that this should work, and it was shown also on several refinements or several experimental data using kinematical refinement. But as we've seen, the kinematical refinement gives relatively high R values. So I took data from these two works. In some case, in this case, it was actually above 25%. There is a visible improvement, but at the level of R value of 25% or even 14% here, the relative gain is say questionable, and the question is if the kinematical refinement does not introduce other bias that could make the results unreliable or difficult to interpret. So that's why we decided to look into the problem using dynamical refinement. And these results, this is the result obtained mostly by Petr Brazda from the experimental side, and also the refinement from here from Prague, and Barbara Gruza, now Oleg from Paulina's group. And what you see here is on the right hand side a difference potential map, so theoretical map calculated as the difference between the transferable anharmonic atom model or spherical atom model minus the independent atom model, and on the right a difference, experimental difference map from the dynamical refinement. At the first glance, the right map looks very noisy, but if you look closely, you'll see that there is actually quite a qualitative similarity. For example, this negative potential here around oxygen is here, and there are also negative potentials between in the bonds, just like there are negative potentials here in the bonds. So it's quite noisy, but it is there. And when the TAM approach is used, so then you see that the difference map cleans up significantly. But what is even more important, and again it was touched by Paulina, and it was very kind of her to leave this to me to show these results, because Paulina mentioned that there was an interesting improvement seen in the calculations using the TAAM with the database coefficients for the atomic for the electron density expansion, and the periodic TAAM, so coefficients optimized from the theoretical data calculated on that structure. And indeed, with the dynamical refinement, this difference seems to be very clearly there. This is so I forgot to mention the material here is 1-methyl uracil, so very simple organic molecule. The independent atom model refinement gave an R value of 7.8%. When replaced with TAAM, the difference map is actually much cleaner, but the R value doesn't seem to be much better. But with periodic TAAM, the R value goes down by 1%, which is something like 15% of the, so one goes down by 1% point, which is about 15% of the original value. So here, the improvement of using not using independent atom model is significant, but only using TAAM does not seem to provide a dramatic improvement. So there is obviously something going on, some let's say deficiency or something that needs to be improved on the approach that that the standard TAAM offers to get the best possible improvement. But so that was about TAM, but let's ask a question: can we go beyond that? Can we go beyond using some kind of database or external source of information? Can we do a refinement of some parameters of the charge density directly from electron diffraction data? Interestingly, here again, like for hydrogen, electrons, at least in theory, provide an advantage over X-rays, and this I tried to summarize it in a couple of these plots. This the plots here show a relative difference in scattering power between an ionized atom like oxygen Y- or sodium 1+ here and the neutral atom. The green curve is for electrons and orange curve is for X-rays. And you see that in all cases for low resolution data, electrons win, and as we would go here, I had to cut the scale here to see the smaller values here, but it is really significantly more sensitive to the charging of atoms, electrons than X-rays. For high resolution, for light atoms, that's not the case. Electrons are less sensitive than X-rays. But already for sodium, a bit heavier atom, we see that there is a significantly higher sensitivity of electrons up to a resolution of about 0.3 reciprocal angstroms, so again, D star. And as we go higher to heavier and heavier atoms, so for europium, for example, there is a clear advantage up to a reasonably high resolution here. So actually electrons seem to be more sensitive to charging than X-rays, and that might give prospect to doing charge density investigations of heavier atoms, for which the change in X-ray diffraction intensities is really small. And now I have the privilege and pleasure to show you some of very recent results that were obtained in this project. And these are some kind of multiple refinement against a few data sets that we collected here in Prague. And so the first one is quartz, a very simple material. This is a work done by Petr Drazda and Ashwin Suresh, a PhD student in our group. And you see, one thing that is important to emphasize here, and that's where I'm getting to my promise to show you that crystal imperfection is very important. These are very, very perfect crystals, void of essentially any defects. They were grown as nanocrystals. This is an image of that. And this is the difference potential map, showing clearly the positive potential on silicon and all the negative potential around oxygen. And already here, with the independent atom model, one can get to an R-ops value of 2.49%. This little m here is here because this stands for merged. I'm showing here R values calculated on intensities that are symmetry averaged, because this is what we are used to when we look at X-ray diffraction data. For dynamical refinement, we cannot do intensity averaging before refinement because different symmetry-related reflections are not expected to have the same intensity due to different crystal orientation. But we can do this averaging after the refinement to get R values that are more directly comparable with the traditional X-ray R values. So we can get to a pretty respectable R value of 2.5%. But when we do the multiple refinement, then the R value goes down to below 2%. So 1.9% is the current R-ops, and even R-all is perfectly fine at 2.1%. And you can see that the multiple refinement, we are still working on comparison with the calculations, so we can't say right now how quantitatively correct the results are, but at least qualitatively we can clearly see the proper concentration of electron density around oxygen and depletion around silicon. But okay, quartz is a pretty simple structure, so the question is, can we go to something more complicated? And the answer is yes. And this is a result that was obtained on Natrolite, which is a zeolite. It's a natural zeolite. It's a moderately complex structure. And here we didn't yet do a full multiple refinement because it is really not so easy and requires some effort. But what we did is the first step in the multiple refinement, and that's so-called kappa refinement, where only charge transfer was refined from cations to anions. So it's still the atoms are spherical, but charge transfer is allowed, and shrinking and expanding of the valence electron shell is also allowed. And what you see here is the difference potential map after independent atom model refinement. And you see there is still quite some signal. The R value gets to 4.7%. And after kappa refinement, we get to 4.1 or 4.14, so a significant improvement of the difference potential map. And this is the kappa refinement static deformation map. So that shows actually the transfer from the transfer of density from the silicon atoms or aluminum atoms here to the oxygen atoms here. So we are again, at least qualitatively or semi-quantitatively, we are getting the expected behavior. And I emphasize that the parameters of the charge transfer, they were freely refined. So this is not coming from the database or from external, from BFT calculation. This is really a result of the refinement against electron diffraction data. And to conclude with the last example, and if I said the previous examples were really fresh, then this example is really super fresh, and I got it actually from Ashwin today morning. So I spent the last minutes before this lecture setting the result up. This is a refinement, again, a kappa refinement on borane. On the borane, so you see this is two, or maybe this is a better place, 2.5 kgs of borane. There are a few interesting observations coming out of this this refinement so far. So here again, you see independent atom refinement, dynamical refinement ends up with an R value of 6.7, which is not too bad. I think we would be happy in many other cases, but it's not as super great as, for example, in Natrolite quartz. But also the refinement is not very satisfactory. These boxes here indicate non-positive definite displacement parameters. So you see that there are quite a few of them in hydrogens, sometimes are negative. And in general, this doesn't look very good. After kappa refinement, this is the difference potential map. And at first glance, you think I forgot to include the potential map, but actually I didn't. You see, there is a negative blob. So this is on the same isosurface level as this. So you see that the difference potential map cleaned up really, really dramatically, and it's accompanied with a significant drop of the R value from 6.7 to 4. And that means that in this case, the kappa refinement really models an important part of the electrostatic potential. And you see that after the kappa refinement, almost miraculously, all the displacement parameters became positive. You see hydrogen atoms refined as anisotropic displacement parameters. Everything is really well behaved. And here again, this is the static deformation map showing this well-known concentration of negative charge in the centers of these boron cages. So this is again very fresh result that will need some more analysis, but it shows that really with high quality data, so that means first high quality crystals, high quality data, and careful data structure refinement, including taking dynamical effects into account, it is possible to obtain first refinement quality that really equals the refinement quality that we are used to from X-ray diffraction, and more important, the sensitivity of the data to effects like charge transfer is sufficient to obtain this information ab initio from the experimental data. With that, I want to conclude. I want to thank to all the people who contributed to this research. So I used results by Paul, by Peter, by Gladys, Ashwin, and Rishi, another PhD student here. But also there's a lot of underlying work that was not explicitly shown, but that was important. So thanks to my group, thanks for funding, and thank you for your attention.
Thank you very much, Lukas, for this excellent lecture. It's time for comments and questions. We'll wait for the first ones. In this high resolution refinements, what kind of completeness of data you were having, and is completeness important in this case, or
yes, yes, of course, the completeness is important. I actually don't have the numbers in my head, but for Quartz, it's high symmetry. It is there. The completeness was 100% thanks to the high symmetry. For Natrolite, I believe the completeness was also very high, close to 100%, if not 100%. And for the Borane, the completeness was also good. I'm afraid I can't tell the number. Maybe Ashwin, if he's listening, he could put in the number in the chat. Yeah, I see he's already typing. But of course, yes, the completeness is important parameter. But if the data, yeah, so I see it was around 86%, so not 100%, but not too bad. If the completeness is not sufficiently high, it is possible to combine data from several crystals to increase the completeness.
Is it common to combine these data sets? I mean, when we are trying to get data in Warsaw, the results of, say, averaging out data is not always success. I mean, the best data sets are better than the average data. So, what do you do? I mean. Do you average data always, or do you prefer averaging data, or you use just the best data set?
Well, the best approach is to average only the best data sets. But this is not what you are asking for. So, well, that is that would require a complex answer. I'll try to make it short. For dynamical refinement, we are not averaging the data. We are combining data, but each of the data sets needs to be refined separately because the crystal orientation, crystal thickness can be different and so on. So we don't average, we combine. If we can get a good completeness from a single crystal, it's preferable for a number of reasons. But sometimes it's not possible, and then we do the combination. But as you say, sometimes there is a bad data set and then it's better to kick it out. Combining a good data set with a bad data set makes the result worse. For kinematical refinement, I've seen many cases where combining several data sets improved the data, I'd say even almost spectacularly. So sometimes if you really can combine good data sets and merge and average together good data sets, then it improves the kinematical refinement significantly.
Thank you. I can see quite a few people writing their questions now, so they will probably get them in a moment.
I have a question in the meantime.
Yes.
How about the resolution? Krzysztof, you said that this is like high resolution, but maybe it's not so high as in X-rays.
Yes, so that's very good.
Do you need high resolution for charge refinement?
Yes, you need a reasonably high resolution. All these three examples that I showed are definitely high resolution, so the diffraction data go above 2 reciprocal angstroms, so better than 0.5. But again, for the Borane, I don't have the number in mind, but that was not extremely high resolution. So I'd say low resolution is not good, but the requirements to get nice results, it's not absolutely necessary to have ultra high resolution like 0.3 or 0.25. So Peter here commented that for Borane, actually the resolution is only up to about 1.3 reciprocal angstroms. So that was actually not very high resolution. For the other two data sets, the resolution is higher.
Okay, Josef Koziszek is asking, is it possible to combine X-ray data and low-order electron data? Do you have 100 K temperature?
Well, so starting from the second question, yes, we try to collect at low temperature whenever possible. It just gives better data in several aspects. Of course, crystal stability is one of them, and the most important. So we have access to 100 Kelvin data. Is it possible to combine this? Well, this was some time ago. This was a very popular approach, combining the CBED, low angle, highly accurate structure factors with higher resolution X-ray data. It's certainly possible. It is not easily possible in our setup, but it is possible to refine against data from X-rays and electrons at the same time. So one could, in principle, pick up only low-resolution electron data and take high-resolution X-ray data and try to combine. I don't think anybody ever tried in the context of 3D ED data. I think better approach would be to use complete data sets, both for X-rays and for electrons. But this is one of the many questions that remains to be addressed and hopefully answered.
Daniel Ugarte, have you optimized the electron acceleration to match the detector quantum efficiency of the camera? I'm assuming that you are using a direct detection camera.
Yes, well, actually, there's a question. For Natrolite and Quartz, it was a direct detection camera. For the Borane, it was actually a standard CCD. So it was not a direct detection camera. But no, we actually hadn't. We used 200 kilo electron volts energy, 200 kV acceleration voltage, and we have direct detection camera that is, say, optimized or suitable for this acceleration voltage, but we didn't play specifically with the voltage to catch some sweet spot of the camera.
Professor Hans-Bert Birgi, were the organic crystals in the last few slides of high quality without special crystallization effort? Suggestions for controlling the perfection of nanocrystals?
So actually, in this part where I showed the charge density, there was no organic crystal. There was this. There was the metal uracil. Yes. So none of these crystals were specifically crystallized. Materials were specifically crystallized, maybe except for the quartz, which we looked up in the literature. We looked specifically for nanocrystals of quartz, and we found it, and we got a sample from an Italian colleague provided. So that was somehow can be considered as on-purpose found materials. But otherwise, these were materials that were obtained without any specific effort on crystallization of perfect crystals. I'm afraid I can't comment much on the controlling the perfection of nanocrystals. It would be good to have such an option, but very often the materials you're getting are product of a synthesis or crystallization where one is not really doesn't have the necessary options to optimize the crystallization. The crystals are just what they are. But I just can't really comment on the possibilities of optimizing crystallization for nanocrystals.
Leonardo Correa, are all the results obtained with block wave simulations? Could multi-slice simulations significantly improve the figures of merit by including crystal imperfection?
That's a good question. This is something we are really now working on. We are looking into the problem. So I hope so, but I don't think that using multi-slice calculation in the refinement is the way to go finally, because doing multi-slice calculation on large crystals that include imperfections would be, even with all the computing power that we have, it would probably be prohibitively long. But we hope to get some insight into the behavior of intensities and their response to the crystal imperfections, and we hope to develop some model that will allow us to correct for this problem. So yes, multi-slice is something that we are looking into right now.
Okay, thank you. I do not see more questions, nor anybody writing next questions or comments. I just want to say that I'm very happy that you do so plenty of different interesting minerals. We study lots of minerals. We have like access to a couple of thousand of natural minerals, and these are fascinating studies. So I must say that I love this application of high resolution X-ray diffraction and electron diffraction on minerals particularly.
Yeah, okay. Just maybe one sentence. Gladys, but also others from our group. We are looking often in minerals because they are just a wealth of unknown structures, microcrystalline minerals. So this is indeed a very interesting field that brings more and more joy and also challenges to our work.
Yes. As I do not see more questions, let us thank to all speakers today.